Okay, I'll switch now for English. So, first of all, just welcome everyone in this new cyber reality. There are several goals of my talk today. What I'm going to present today, it's not a final stage of a big project we're doing with Nikita Nekrasov, just some partial results. But mostly what I would like to do, just to see how we can live in this new reality without seeing each other every Monday, instead meeting at this Zoom place. Actually, I don't know what's the best way, and I try to find a substitute for a blackboard, because I prefer writing on the blackboard instead of just passing through already written text. I don't know what is the speed of this presentation. In all days, I knew you have a 1 hour talk, you have to prepare 20, 30 transparencies, and that's it, because every transparency takes about 3 minutes to discuss. What is going to be today, we'll see how it works. Okay, this is just preliminary. I also would like, before I start talking about this.
Игорь, извини, можно еще раз повторить, всем выключить микрофоны, кто в данный момент не говорит.
Okay, again, please. Probably I can do it from my side. I can mute everyone. Can I do it?
Ты должен уметь выключать, наверное, но... А с твоим звуком, ну, у меня тоже не очень хорошая слышимость, я не знаю, в чем пока дело. Может быть, это только у меня.
Okay. Again, I asked everyone to mute their own microphone, because otherwise it's going to be very noisy and disturbing.
Нет, там где-то справа под Manage Participants должна быть кнопка Mute All.
Mute all. Okay. No, I don't want to touch anything, because otherwise I'll mute myself. Okay, so just one announcement before we start. This new reality gives us new opportunity. In particular, Andrei Akunkov wants to give a mini course for our students, probably not only for students. So I'm just announcing this. He will send me a title and short description. The only problem is to find a proper time when this course can be given, because right now it seems that everyone has so many meetings that it's hard to find a time. Probably Pasha can help Andrei to also put this mini course on recording. Okay, so right.
Да.
So, okay.
Я понял, я иду.
Что такое?
Это все вот проблемы с микрофонами. Кроме того, я не знаю, там несколько человек с камерой включены. Может быть, это тоже замедляет, но могу понять.
I don't know. But microphones are very disturbing. Okay. So, what I will talk about? I will talk about the sigma model, which is one of the most classical and fundamental models in the field theory. Two-dimensional sigma model, it's about maps from a source to some target space. And we are looking for critical points of the action for this model, which is given by the simple integral. You have a metric G, metric on the source. And there is also a metric on, so this is a metric on the source, this is a metric on the, what I'm talking, metric on a target, this is metric on the source. So you are just taking nm of x, d mu x, and d nu xm. If you choose a system of coordinates on this space at mu nu, dx mu, dx nu. This is the so-called general sigma model. I would like to stress that the properties of solution of these equations of motion that I haven't write yet very much depend on a signature of a metric on a source surface. So we're talking about two-dimensional model. So sigma is a surface. And in the talk, I will mostly speak about, only speak about sigma being just a torus with a certain metric on it. But what is important, this metric is Euclidean. So two more cases are of interest for me, would be just ON model, when the target is just Sn minus 1 with canonical, with induced metric on it, metric induced from Rn space. This is one source. This is one model I'm going to consider. Or also principal chiral field. And principal chiral field is when the target is a simple Lie group with invariant with respect to right and left translation metric on it. For simplicity, I will mostly consider the LN case or ON case. In all cases, the metric G metric is defined as trace of dg G inverse square. This is two cases I'm going to consider. Principal chiral fields ON model are considered as integrable models since the famous Pohlmeyer result when he found for equations of motion for Pohlmeyer found zero-curvature representation for ON model. He didn't call it zero-curvature representation. Moreover, he was not aware how to write it explicitly. His result was actually clarified by Zakharov and Mikhailov. and Mikhailov a bit later, when they found that a wide class of relativistic models can be presented in the zero curvature form, namely for principal chiral field. They found the representation that principal chiral field can be written as the zero curvature condition for u lambda plus 1 commutator with dz bar plus v z lambda minus 1 commutator equals 0, where u is dz g inverse and v is dz bar g inverse. I have to stress that Pohlmeyer, Zakharov, Mikhailov, and most of works related to integrability of sigma model, well, they were concerned actually with the case when the signature of a metric on the source is 1 minus 1, so it's hyperbolic wave type equations. The passing from wave hyperbolic to elliptic case is very simple. You just go from x plus t to z, x minus t. So x and t are real coordinates. In the hyperbolic case, you pass to light cone variables x plus t, x minus t. And to pass to elliptic equation, you just replace z by z bar. This is just pure algebra and nothing specific. We'll see the difference in a minute. How drastically, yes.
What does it mean, zero curvature representation? Is it every...
Okay,
I
zero
just don't know.
Representation means the following. You have a space. Now we have two-dimensional space, x and t. You have a curvature, which is d over dx plus ax, d over dy plus ay ty. So a curvature in some bundle, trivial bundle, A of t, is defined by these operators, covariant derivative in x direction, in t direction. And now as you are saying that these two derivatives in x and y commute, so the curvature of this connection defined by u and v is 0. That's all. This is, if you wish, this is just the equation that I can see defined as a definition of zero curvature. But actually, it's
so lambda is an auxiliary parameter, so that this should hold for every lambda, is that?
Yes, that should be valid for any lambda. Okay. So we'll see in a minute what it means, because just if this expression, this zero curvature equation is satisfied for all lambda, clearly it's algebraic, it's rational in lambda, so you should require that residues of this expression vanish. So you have dzu equals 1/2 commutator of uv, if I'm correct. dz bar u plus v, and dzv equals 1/2 commutator v and u. So just if you subtract these two lines from one another, that implies that u has a form d z g inverse for some matrix g, v is d z bar g inverse. And from this equation, it follows that dz bar of u equals negative dz V. This is what we call zero curvature principal chiral field equations. And this equation and the condition that U and V are currents for some matrix G is exactly the compatibility, is equivalent to this equation that should be fulfilled for all lambda. Any questions?
When you say this equation, we don't see which equation you point to. So maybe you give them names or stars and you call it not this equation, but say star equation, just to follow easier.
Equation, the zero curvature equation, is equivalent to the equation with two stars and the condition that U and V are currents of some function G, which is a function of G and Z bar. Okay, now you see it?
Yes, yes, yes.
Okay. So, but you see the equation by themselves, they have the form of the conservation laws. Actually, from this zero curvature equation, you can obtain not just one conservation law, but infinite family of them. And that the existence of infinite family more or less was what in mind when people say the equation is integral. My goal is to show more. I want to prove that the equation of motion for principal chiral fields, and more generally to some extent, the arguments I am going to present are so general that it means more or less algebraic integrability of all elliptic versions of equation admitting zero curvature representation. But first,
sorry, I didn't understand why is it obvious that you have infinitely many integrals.
Sasha, at some moment I will explain, because actually that's true. The equation two stars can be written for the whole operator U with the lambda parameter. Okay, let me just postpone an answer on your question a little bit later. Okay, you will. So, but what's the first place? Before, let me just say just a few words before I'll proceed. The elliptic, so as I said, for most work you find in vast literature, the metric on the source was hyperbolic. Elliptic cases was also considered, and the most remarkable result was obtained by Hitchin, who considered ON model on a two-dimensional torus, S1 cross S1. So he was interested in harmonic maps of two torus to three-dimensional sphere. That was his main result. And he proved what I call algebraic integrability. What he proved algebraic integrability of this equation using SU2. SU2 principal chiral field. Chiral field is the same as O3 O4 model. So what was the key step in his proof? First of all, observe that this compatibility condition, the zero curvature representation, this star, thanks Senya, now it's easy for me to refer to make a reference to certain equation, is the compatibility condition of two linear problems, dz minus u over lambda plus 1, psi z bar lambda equals 0, and dz bar plus v over lambda plus minus 1 psi z bar lambda equals 0. So the connection with coefficients u and v is flat. That means there is a basis of holomorphic sections that can be seen as columns of the matrix psi. And the solution of this equation exists for all lambdas functions of lambda. Sasha, now I can give you just remark how you get the right. No, too early. An answer on.
And you didn't define the notion of algebraic integrability, did you?
I'm going to define.
You did not. You said you're talking about the proof of algebraic integrability, but you didn't define it, right?
I'm going to define together with the proof.
Okay.
In a second, it will be seen. Okay. So.
Excuse me.
Yes.
Do you mean that psi depends on lambda holomorphically or
no.
As a smooth function?
No, it's for sure it is. It is holomorphic outside plus or minus 1.
Okay.
It's the equation analytically depending on the parameter. So
okay.
Is holomorphic function outside of lambda equals plus minus 1. Okay. So suppose now we are on torus. So u z plus 1, z bar plus 1 is periodic. U z bar. U z plus tau, z bar plus tau bar equals u of z bar. So we're actually on the torus. So this is 1, this is tau. And in case of u and similar for v, periodic, the solution has monodromies around cycles of this torus. So you can define V1 is of lambda equals psi bi, let's call it bi psi of P1, this is psi z plus 1, z bar plus 1, lambda psi z bar, lambda inverse. So this is a monodromy around the first cycle. You can similarly define the monodromy around the second factor. And you can define the so-called Bloch spectral curve, which is the characteristic. This is defined. The spectral curve defines actually eigenvalues of these monodromy matrices. So determine mu times 1 minus b I of lambda. And since the matrix, the fundamental group of torus commutative, this matrices bi, b1 and b2 commute. So actually these two analytic curve, because b is some holomorphic function of lambda outside lambda equals plus minus 1, but having essential singularities. So it's analytic curve. And the key step in the proof of key statement of Hitchin is, okay, he considered specifically SU2 case. So this is the equation of the second order in mu. So he proved that this curve, gamma Bloch, if you consider its projection on lambda plane, has only finite number of branch points. Let's call them lambda I. So you can define an algebraic spectral curve. So given by the equation mu square, mu hat, it's another mu hat equals lambda minus lambda I product. You get a hyperelliptic curve of finite genus. Lambda I are branch points. So this is the points where this equation, the equation for defining eigenvalues of monodromy matrix, Flaquet multipliers, has 0 of odd multiplicity. There is only finite number of them. And the result of Hitchin in geometric terms, he wrote that probably one can write the formulas, but it was just as outside of his intention. So what he proved that a solution of these harmonic maps of two torus to S3 are uniquely defined by hyperelliptic curve. This is the curve defined by this equation, and a divisor, or a point of the Jacobian of this curve. The arguments of Hitchin was very specific to SU2 case. He had never considered any principal chiral field for even for SUN or other groups.
Sorry, can I ask a stupid question? I'm a little confused about the definition of spectral curve. So somehow you're right. Is it given by one equation or two equations?
You mean this is just one equation because this breakpoint coincide.
No, but you have this I. So I'm confused about. So I mean, so first of all, in what space are you writing the equations?
This is not the same. DJ. So
no. I'm talking about the original definition when you write determinant of mu times 1 minus.
So okay, this is where I write this equation in C2 with coordinates mu and lambda.
So and so I is I is you fix I.
For each I, I mean for the monodromy around a cycle.
So there are two spectral curves.
There are two spectral curves, but they coincide because this monodromy commute, and actually the curve is the same. You can start with any of them.
Is this obvious? I mean, I don't understand why commutativity implies that these two curves come.
They are not the same, isomorphic.
Yeah.
The eigenvalues are different, but they behave in the same way because they commute.
B1 is equal to 1 identically, and B2 is something non-trivial. Then this curve is not isomorphic.
Actually, you may think about everything. You have B1, B2, and lambda. Actually, you can exclude lambda and have in the space B1 and B2 the relation between eigenvalues. Hello?
Игорь, я тебя почти не слышу. У меня, я не знаю, как остальные, у меня треск все время. Но в частности я прослушал, что конечное число точек ветвления. Это что это? Условие чего-то?
Нет, это...
Sorry, yeah. The finite number of branch points. Is it condition of something or what?
No, it's the main conclusion, the main result of teaching. That for
from what it follows? What is the reason?
The reason is that we are dealing with elliptic equations first, and second, that the source is compact. And actually, the goal of my talk, somebody should switch off the microphone. The goal of my talk to explain in a very basic way, simple way, why it is so. But I will speak not in terms of O3 or 4 model. I will talk about principal chiral field for any group.
Does it mean that B are some polynomials or?
No, it means as in the theory of for example, in the theory of KdV, that actually the curve defined by, this is analytic equation. The equation is analytic. D is analytic function, not algebraic in any sense. But it means that that this equation, if you look at it as a double-sheeted cover, has only finite number of branch points, and the rest is singularity, like nodes crossing. So what we are talking about is that normalization of this Bloch-Flaquet curve is algebraic. It's like, Andrei, like in the spectral theory of Schrödinger operator, finite gap solutions are solutions such that only finite number of eigen.
Yeah, well, that's what I had in mind, but then it depends on initial condition. Only for some very specific conditions, you get this finite gap family, and where it's hidden here.
Again, the hidden here in this setting, this is elliptic problem. And this is specific for elliptic problems. They are all algebraic integrable. All spectral curves that appear in this theory, they are all algebraic. Okay, this is what my main point today, that is what I want to explain. And the arguments you will see is very simple and very general. But first, let me just explain the first appearance of the ellipticity and compactness is in the following. You solve the equation of motion for u. Okay, I can write it. D z bar of u equals commutator of 1/2. Probably I'm up to a sign here. I don't remember. Should I go back? It doesn't matter. Okay, it doesn't matter. In any case, what this equation implies? This equation implies that dz bar trace of uk equals 0. So that means in the hyperbolic setting, you will say that eigenvalues of u are functions of the second variable, the z bar constant. So here you get that this is equation for all k. This implies that eigenvalues of u are holomorphic. On the torus. So that means they're constants. Again, ellipticity plus compactness implies that eigenvalues of u are constant, and the same for v. That means that if in generic case when these eigenvalues, the method is diagonalizable, eigenvalues are distinct, you can write that u is phi plus k plus phi inverse k plus ij is a diagonal matrix I delta ij. Again, this is luxury. You see, in the ordinary theory of principal chiral field, you have only that eigenvalues are functions of one variable. Now we have that they're constant. The same for v. Phi minus k minus phi inverse. With this is generic form for u and v. Okay. Now, what is the basic idea underlying why everything is algebraic? The first step I want to do is to say the following. Principal chiral fields equations can be extended to a hierarchy. So if G is Z, Z bar is a solution, what I mean that you can define actually a family of solutions depending on T. Surprisingly, I looked in the literature, asked some experts, and it seems that it was just a common statement. Okay, you have an equation admitting zero curvature. There should be higher floors on the space of solutions. Nobody wrote zero curvature representation for this equation, and that's what I'm going to do now. So I want to define deformations of zero of principal chiral fields.
What is T here? Is it one coordinate or infinitely many coordinates?
It's infinitely many coordinates. They are labeled by, in the example, as I will not construct all of them. They are labeled by I, which is going from 1 to infinity. and also by a diagonal matrix. So this is the set of variables here. Okay.
Sorry, what is this capital J?
J is a diagonal matrix. J.
Diagonal matrix with values like which are what?
I take any representation like I wrote here. For simplicity, let's again, my argument doesn't rely at this moment on specifics of a group. So I will talk about G being G, L, and C. So just complex m-dimensional matrices. And I take fundamental representation. So it is in the same space, Sasha, as eigenvalues of U and V.
But I don't understand. So that means that there's some continuum number of parameters or what? So.
Yeah, it's unlike there is continuum number of parameters. But as always, you see, it's not exactly continuum because there is only n linear independent diagonal matrices. But this is how they came. Let me just define them, and we'll see. Okay. The first statement, the first step, lemma. Let U and V be a generic solution of principal chiral field equation for ZL and C. That means that this U and V has such a form, so K plus and K minus, two diagonal matrices with distinct diagonal elements. J, I not equal to J, are fixed. So let be a generic solution. Then there exists a formal solution. A formal solution to the equation so solution to this system of the form psi plus, so there exists a formal solution psi plus, which is a function of z, z bar, and lambda, of the form phi plus. Phi plus is the same as a matrix of eigenvectors of U, z, z bar, times some psi s of z, z bar, lambda plus 1 to the power s, exp z k plus lambda plus 1. So this is like WKB method. So you just plug in this equation, this formal series, and you get a recurrent system of equation K plus commutator psi s plus 1 plus, commutator equals dz psi s plus phi plus inverse dz phi psi s. This is a recurrent system of equation for S starting from -1 and to infinity. You can solve it recurrently, namely, if you take S equals -1, that implies that psi 0 is diagonal. You just choose psi 0 to be diagonal matrix. Oh, okay, so and recurrently, this equation, this recurrent system of equation.
Right, I assuming that K plus is generic in some sense.
As I said generic means that this is diagonal matrix with distinct diagonal elements. That implies that psi 0 is diagonal. And you can recurrently solve this system, assuming that on each step, you know psi s of diagonal part, of psi s is known. Like here, we know, like for s minus 1, we know that psi 0 is diagonal, means that of diagonal part is 0. Suppose inductively that psi s is of diagonal part of psi s is known. Then the left-hand side of this equation, this part, has 0 elements on the diagonal. So you solve for diagonal elements the equation in the right-hand side. You setting it to be 0 diagonal part. You get the equation that defines psi s completely. You define the diagonal part of it, uniquely up to adding a anti-holomorphic function. After that, when you know the psi s completely, you solve for psi s plus 1 of diagonal part, which is just very simple. And you continue. So there always exists such a formal series. And it is unique from the construction up to multiplication. So as a solution of the first equation, dz minus u lambda plus 1 psi plus equals 0, you find, and this is the recurrent system equation equivalent to this first equation. You find psi
Igor,
plus.
Igor.
Sorry, yeah.
Sorry, I don't understand why do you say that diagonal part is known when you insert.
Okay, Andrei, let me repeat. Let's start with s equals -1.
Yes.
From the equation, there is nothing on the right-hand side. So we see that psi 0 commutes with k plus, and because k plus is generic, we conclude that psi naught must be diagonal.
Yes, okay, this is clear. Okay.
So that means we don't know this diagonal part here. What we know that of diagonal is 0, so the of diagonal part is known.
Okay, yes, it is 0. Okay. Next
now,
step.
We're going, and this is our assumption of the induction, that on each step in the equation written, in this equation, we know of diagonal part of psi s. Now, the left-hand side of this equation has 0 elements on the diagonal.
Mm-hmm.
So we get the elliptic system, first order elliptic system of equation for diagonal element of psi s. We solve it. And its solution is
Diagonal is
we,
solved. I see. Okay. Okay.
and this is unique up to adding anti-holomorphic function,
Okay.
the kernel of dz. Okay?
Okay, thanks.
So you first find diagonal elements of psi s. After that, it is fully known. And you solve for psi s plus 1 again off diagonal path. This is just you divide psi s plus 1, s plus 1 ij equals what you have in the right hand side divided by ki minus 2j. It is just explicit.
Okay.
And you proceed, so you solve it. And the solution is known up to multiplication psi plus prime. You can multiply by any diagonal matrix with anti-holomorphic, which is anti-holomorphic F diagonal, anti-holomorphic, and its formal series in lambda. That's all. This is just corresponds to this ambiguity in the definition of the diagonal part. Now, if dz bar plus v lambda plus 1, lambda minus 1, if this operator commutes with dz minus u, you have that psi plus is again the solution to the same system. That means that psi, you take any solution, apply, you get this is f of z bar lambda, and you can construct the solution to the whole system just after simple gauge transformation. Psi plus would be psi plus prime x minus integral from z bar f z bar lambda. That's all. This is the solution. And the solution by construction is unique. Again, somebody please, Andrei, it's probably you. Just switch, mute your microphone. So we get that psi plus is unique, exists, and unique up to multiplication by a constant matrix, diagonal matrix, which is formal power in lambda plus 1. This is the first statement, that given u and v, that a solution of our system, we uniquely define psi plus. What is the next step? The second lemma. For any I and j, Sasha, this is just any matrix, diagonal matrix. They exist given any formal series of this form. So take now any formal series. It's very simple to show that given such a matrix, there exists a unique W I and j. This would be a matrix function whose coefficient depends on zz bar and lambda, and its dependence in lambda, it's just polynomial in lambda plus 1 s from 1 to I, w I j s. So this is just matrix coefficients here. So there exists unique wi such that wij applied to psi plus, so for any formal series, minus psi plus j divided by lambda plus 1 to the power I, psi plus, equals O of k, or O of 1, exp k zk lambda plus 1. This is the statement that for any, you start with any matrix, G diagonal, you multiply psi lambda plus 1. So what you will get? You have this formal series. You multiply it by, from the right, by matrix. You get some expression. This is commutes with exponent because we have diagonal terms here. So you get, instead of regular series from 0 to infinity, psi plus, you have now Laurent polynomial in lambda plus 1. And the statement is that there exists a unique Laurent polynomial in lambda plus 1 inverse such that this difference is zero modular regular series in lambda plus 1. This statement is very simple. You just plug in and you cancel all singular powers of lambda plus 1. Is it clear?
Who is J? Who is J? Any diagonal matrix?
Yes. Okay, let's see. Take a diagonal matrix. Substitute. What you will get as a term lambda plus 1 in the power negative 1. You multiply psi plus by j. So you get the leading term would be psi. You will get phi. So you get phi plus the leading term psi 0 g lambda plus 1 to the power I. This is what you get from this part. You're writing this is equal to Wij, the leading coefficient in this expression, S equals I, times lambda plus 1 to the power I phi plus. You solve it. Okay. Psi 0. So we get that the leading term would be I, J, I. This leading coefficient would be phi plus J, phi minus. So it's a matrix commuting with U. That's all. That's why you can start with any diagonal matrix, and then you recurrently find all other coefficients. Now, the next. So what we start with, we define U, V, with the help of U, V, that are solutions of our system. We define psi. From psi, we get W, I, J. For any I and J, we get some polynomial in lambda plus 1 matrix. Now I define the equation dij. So I define the evolution of my system with respect to time ij of U equals commutator lambda plus 1. Let me just, I divide it by lambda plus 1. And that equals to commutator dz minus u lambda plus 1 Wij. And similarly, I will define dTij of v lambda minus 1 equals commutator of dz bar minus v lambda minus 1 Wij. Okay. This is those who are familiar with the notion of KP hierarchy. They used to, okay, let me just slowly. So what I did, starting from UV, I defined W. So W is a function in a very complicated way. I don't read, but it's a function of U and V. So if I plug in this UV, I have a closed system of equations. Why this system of equation is well defined? A priori, it's not clear because the right-hand side, which I just underlined, a priori is polynomial in lambda plus 1 of degree lambda plus 1 minus I. Minus I because Wi has pole of order I, but the leading term commutes with U, so this is a priori the pole of order of the right-hand side. Okay, so in order this equation to make sense, one needs to prove that the right-hand side of equation dot is also a polynomial in lambda plus 1 of the first order. It's clearly, if it's a first order, it just has in the form lambda plus 1 because all matrices are 0 at the infinity. That's why we need to prove that the right-hand side is a polynomial of the degree not greater than 1 in lambda plus 1. This is similar how one proves correctness of definition of the commuting flows in KP or KdV theory. You need to prove that certain commutator of operators has degree less than n. Usually, people know only the solution to this problem in a scalar case, thanks to Gelfand and Dickey. But it works only for scalar operators, not with operators with matrix coefficient. The way how I proceed right now, this works in much more general setting. So how to prove that the right-hand side has right degree? A priori, right-hand side is a polynomial with matrix coefficient of lambda plus 1 minus 1 of degree I. Let's apply this polynomial d z minus u lambda plus 1 commutator wij. Let me apply to psi plus. What I'll get? I'll get, okay, the term when you apply dz minus u to y, psi plus is 0, so you get wij psi plus. But according to our definition of wi, you get, this is psi plus j to the power 1 minus lambda plus 1 to the power I plus O of 1 times exponent. From this equation, it follows that this is equal to u lambda plus 1 applied to this O of 1 exponent. So that means that if I apply to psi plus this expression, I get something of the order 1 in lambda plus 1 inverse. That is possible only when this matrix by itself has a pole of order 1. So the correctness of the definition is clear after that. And in the same way, one can prove the same argument. Show that dTi j minus w dtk j prime minus w I j k g prime. So all these flows commute. Again, you need to prove that this commutator is vanishing. So apply to psi plus, and you will see that this is, as a pole has no poles at all at points lambda plus 1, so it vanishes at infinity, so it must be identically 0. This is how typically one proves the existence of commuting flows and their commutativity. Now, so in this way, I define deformation G, Z, Z bar, because the equation commute I can solve and get G, Z, Z bar depending on T. And for all T, this is a solution of my principal chiral field equation. Now let's define G is d over dt. So let me just for any time t is a collection of infinite number of variables. Let me take any and differentiate. If you have a system, a solution of certain nonlinear equation depending on parameters, and you take the derivative with respect to this parameter, you get a solution, and then set t equals 0 is a solution of linearized on the background of G Z Z bar. So you take any initial solution of this system, you deform it along T, you take the partial derivative, you get a solution of the system to, I'm writing for principal chiral field dz bar G equals dz G, G inverse dz bar G plus dz G inverse d bar G plus dz bar G minus 1 G plus dz bar G inverse d G. Okay, so what we have, so G is a function of Z bar. This is a linear system, this is a linear equation for G whose coefficients are our known functions. So we have a linear system with certain coefficients. This is elliptic system of equations. Elliptic linear equation with periodic coefficients has only finite number of solutions, because any elliptic system of equation on a compact manifold has a finite number of solutions. Therefore, this is infinite number of flows I constructed I defined, only a finite number of them is only finite number of them are linear independent. So we can choose a linear combination of these flows such that the solution would be stationary with respect to this flow. So I can set that the left-hand side of this equation for some t or their linear combination, that doesn't matter, is just zero, because these flows are linear dependent. So what we just proved, that here, for generic G ZZ bar, which is a solution of the principal chiral field equation, there exists a matrix psi ZZ bar of some order. I don't know what's the order of pole of this matrix, but it's in any case, it's finite order S from 0 to some I W S ZZ bar, such that together with the equation of principal chiral field equation, the equation dz minus u lambda plus 1 W equals 0, dz bar plus v lambda minus 1 W equals 0. So what we just proved, that there exists a matrix, polynomial function in lambda plus 1, such that it satisfies this equation. It satisfies the equation. Okay. That implies that the determinant of K minus K identity matrix minus the characteristic polynomial of ZZ bar lambda, which is R of K lambda, is ZD bar independent. So we constructed for any generic solution, we constructed an algebraic curve, because this is an algebraic, it's polynomial in K and it's polynomial in lambda plus 1 inverse. So it's algebraic by construction. And again, what are the main points of this of the proof? You include your initial equation into the hierarchy. You need to have a Lux representation or zero curvature representation of this hierarchy with a spectral parameter. That was essential because we need to conclude that W is polynomial. Then, from the ellipticity of the problem and compactness of the source, you conclude that only finite number of flows are linear independent. And if they're, so you can just take a variable, which is with respect to which is everything is stationary, and you get that the characteristic polynomial of corresponding W is a constant, is bar independent. With some additional work, you can prove that gamma, the corresponding UV with sign gamma and divisor of poles of the eigenvector of W, there in general, they uniquely defines U and V. This is called spectral transform. Okay. Any questions so far? Hello? Sasha? Hello?
Yes, I'm here, but
So, algebraic integrability now, what I meant is the following, that any solution of our periodic problem on a torus of principal chiral field equation defines you an algebraic curve, and generically the solution is uniquely defined by this algebraic curve and the point of the Jacobian of this curve. That I mean by algebraic integrability. It's far from the, and it's not the end of the story, but the answer on the following questions I'm going to discuss, they are all in realm of algebraic geometry. So nothing from analytic theory is left. So you are dealing only with questions, some problems about spectral curves and divisors. So everything becomes pure algebraic. That's what I mean. And my arguments, as you see, as all of you see, hopefully, I don't rely on any specifics on any group. They mostly use only ellipticity and existence of only a finite number of solutions for linear system. They should work in all cases. What is the main challenge? What is the problem needed to be addressed? Problem. Starting from any curve, family of curve and divisor, we may construct U and V. So, family of curves depends on Lie group. And that should be worked out in every case. But this is not, for example, if or n principal chiral field. The matrix U and W are skew symmetric. That implies that they exist on a corresponding spectral curve. They exist a holomorphic involution. That in terms of eigenvalues, k lambda goes to minus k lambda. This is obvious. And the same, these type of problems are not very hard to solve. The major problem is starting from arbitrary gamma and d is in such a family. One gets quasi-periodic solutions to the principal chiral field, to the principal chiral field equation. And the constraints on gamma. So which curve gives you a periodic versus quasi-periodic solution? It's a transcendental equation because the answer is given in terms of periods of some second order abelian differentials on the curve. And because they are transcendental, it's very hard to actually to say, are there solutions at all? Can you find a spectral curve that gives not just periodic, quasi-periodic, all of them give you quasi-periodic, meaning that the answer will be given in terms of abelian function on the torus, and you have two, and you have direction, so your function of ZZ bar is a restriction of this abelian function on the high genus torus onto the straight line generated by some vectors that are periods vectors. And to make these periods vectors lie into the lattice of the matrix of B periods of differential, it's transcendental. That's why actually teaching never succeeded in full in solving the problem I said, namely maps of torus to S4. He said that all solutions are, if they exist, they're given by algebraic curves of final genus. He succeeded to show that at least for spectral curves of in genus 1, 2, 3, up to 3, there are curves that gives periodic solutions. And left open the question, are there solutions for higher genera of spectral curves? I was planning when I prepared this talk as a second topic to discuss. I prepared an expected solution to this periodicity problem we found with Nikita. Namely, it turns out that solution to O n models with n odds, namely to O to m plus 1 model. Periodic solution, this periodicity constraint can be explicitly solved. And so periodicity condition. Unlike this, you see, this problem is very familiar to anyone working in the theory of integrable system. For example, there is no any explicit way, for example, single out hyperelliptic curve corresponding to pure periodic potentials, periodic solutions of KdV equation. That can be done, and that was done in discrete case. Andrei is Marshakov, I mean, is know that hyperelliptic curves corresponding to periodic solution, periodic Toda lattice are of very specific form. There is a specific ansatz that you cannot do in continuous model. It was a surprise for us that the answer for this model, for sigma model condition, are solved in terms of elliptic Algebraic curves. So all periodicity constraints or all curves giving periodic solutions for elliptic O to M plus 1 model are curves defined by very explicitly by pi delta ij minus sigma xi minus xj alpha sigma xi minus xj sigma alpha 1 minus delta ij. So you take a matrix whose off-diagonal terms are certain expression in sigma functions. You write the characteristic equation for this matrix, sigma of m, and you get a curve that is called Algebraic curve, k minus L of alpha. And it turns out that not any Algebraic curves with involution give solutions to O n to m plus 1 model. How Algebraic appear in the theory of sigma model? I don't know. I have no explanation, except whenever you see something, sooner or later you will find Algebraic system. That was my topic for the next topic I wanted to explain, and actually everyone knows when which Algebraic curve have involution. Of course, any hyperelliptic Algebraic curve is a curve with involution. But this is curve corresponding to elliptic solutions to the KdV equation, and they are stationary. It turns out that curves with involution that solve our problems are, so this is the same as turning points of elliptic Algebraic system. Namely, this is when pi equals 0. So take any configuration of particles, xi, and let momentum to be 0. You have a matrix with 0 elements on the diagonal, and the characteristic equation is the curve explicitly defined, and it gives a solution to sigma model. But I'm afraid that at least I'm not ready to continue and explain why and how it is related to sigma model. So my goal for today was to present arguments explaining what algebraic integrability means for elliptic models. So if you have questions, I'm ready to answer. Anyone?
How is alpha in Algebraic curve is related to lambda in principal chiral field?
There is no direct relation. So it's the construction from the corresponding curve. Okay, I have to confess that in the theory of sigma models, I know at least I need. Okay, Anton, maybe you can mute yourself.
Я не знаю, как выключить микрофон. Я не вижу тут.
А там где-то около микрофона стоит. Окей, я сейчас тебя выключу.
Хорошо.
А, это не то. Это кто-то другой, это у Погребкова. Дело в том, okay, there are three spectral curves. One I defined from the beginning, the spectral curve which appears as a characteristic polynomial of the monodromy matrix. It's analytic curve. The other spectral curve I defined as a result of this passage to floors in pure algebraic terms, W, which is what before. These two curves, it's not trivial, but that can be proved that the algebraic curve we defined at the end of the story about here. This algebraic curve defined by this equation is a normalization of analytic curve. So these two curves are the same. There is a third approach, which to construct solutions without use of any zero-curvature representation. Once, maybe a year ago in our seminar, I spoke about constructing solution to sigma model via linear operator with self-consistent potential. It's a difference. And this is another curve. In this curve, in this approach, there is no zero curvature representation. There is nothing. You just directly construct. And actually, and I don't know the connection between the third, I mean, this is Fermi curve approach and lambda approach. I don't know, simply at this moment, there, at least if the relation is, does exist, it should be very non-trivial because it was observed by Hitchin. That actually, if you want to construct, solutions to O T, so the and model with values, sigma model with values in two-dimensional sphere, there is no spectral curve at all. It becomes trivial. The Fermi curve is highly non-trivial and exists. And this is, okay, that should be subject. This is an interesting question, because in the same problem, you cannot have too many different spectral curves. They should be related to each other, but how? It's not clear. So the answer for your question, Anton, I don't know. There is no any relation between alpha and lambda.
Let's see.
Okay.
I wanted to ask, are those extra flows defined by matrix J Hamiltonian? And if yes, what are the Hamiltonians?
The Hamiltonians, the density of the density of Hamiltonians would be the answer, Pasha, in this specific question, I haven't checked, but I'm quite sure, knowing the previous, from the previous experience, yes, they are Hamiltonian because the approach works, and the Hamiltonians for all floors are the density are just these coefficients of the expansion of this formal Baker-Efficient function, as usual. So you choose psi s would be just densities of the corresponding limit domain, I believe.
Thank you. So maybe I want to ask something unrelated. So is there any description of periodic solutions for Schrödinger equation in terms of some explicitly written curves?
You mean
Like
usual nonlinear Schrödinger equation?
No, to just a one-dimensional Schrödinger equation.
Yeah. It's a linear or nonlinear Schrödinger equation?
Sorry, not Schrödinger, but KdV. Sorry.
No, again, okay, let me just say the answer. No, there is no explicitly, there are some explicitly known, like Lamé curves. We know that for Lamé curves, but they're, so if you take, in terms of eigenvalues, no, the answer is unknown. But there are good news and bad news. Bad news that actually you cannot write explicitly a curve that gives periodic solutions of KdV, unless you can solve the eigenvalue problems for linear Schrödinger equation. But what is true, if you know one equation, then you can find the other curve integrating very simple linear system of equations. So if you know one point on this locus of periodic curves, then you more or less know everything. The problem is to find at least one. More precisely, what I said is the following. This is just spectrum of your Schrödinger equation. Y squared equals the product of lambda minus lambda I. So lambda minus lambda I from 1 to 2. It's some hyperelliptic curve. So on this curve, there exists a differential dp, which is radical of r. This is the polynomial r in lambda. E to lambda to the power g plus sum of e I lambda g minus I d lambda. So this is hyperelliptic differential with pole of order 2 at infinity, and you normalize it by the condition dp integral from, say, lambda I to I plus 1, lambda 2I equals 0. So you solve this linear system, you define AI. The condition that the differential is periodic is that the integral from lambda 1 to lambda 2I of dp is integer. Of course, it's highly transcendental equation. How to solve it? Nobody knows explicitly. But if you know one solution, you can define a flow dk lambda I equals let me call this polynomial Q of lambda. It's a polynomial lambda depending on all the other roots of the polynomial. So you write the equation dk equals Q lambda I to the power k divided by Q of lambda I. Just take the evaluation of this polynomial lambda to okay, so this is a linear system, very easy written, you can solve it. And this is the floor in the space of hyperelliptic curve that doesn't change the periods of this differential. And everything becomes here just pure algebraic. So if you know one point, you know the tangent space to the whole periodic curves, but that's all, it's up. Except maybe it's the first example when you can explicitly write periodic curve. This is example found in our study of sigma model.
Thank you. So is there a statement that all curves corresponding to periodic solutions are this Krichever curves?
Not. They are all in a certain class of solutions. Namely, you can define actually I define a spectral curve, and in most cases, in some cases, it is irreducible. In some cases, it is reducible. Its normalization consists of two parts. So the explicit answer I gave is for the case of reducible spectral curves. But again, as I said, when you know at least one point, then you can move on and have, to some extent, relatively explicit description of all the curves. So what we found a nice big family of curves giving periodic solutions. Then you deform.
Thank you.
Okay, if there are no more questions, I think we can stop. What will be in a week? You will get, so far it's not clear, but okay, sooner, maybe at some moment, if there would be an interest, I will explain the spectral transform and its relation to elliptical, how elliptical algebra method comes to. Okay, any questions?
Okay, thanks.